All right, let's go through the napkin ring problem, which is a really fascinating little puzzle that is a good example of using this shell method for finding volumes. So I'll take a minute first to just review the shell method. So imagine you have a curve, f of x, that generates this region on this interval a to b. And imagine that we are interested in trying to find the volume that results from rotating this region around an axis. Let's say right now it's the y-axis that we're going to rotate around. So in order to find that volume, you can calculate it this way. You break it up into little pieces. Imagine you take this height of the function at one particular x value based on the function, and from that height, imagine generating this shell wall that's produced as we rotate that single darker blue rectangle around the y-axis. So then that value x, so the value of x can take any particular value such as this x bar sub k. That just really is referring to a sample point on this little subinterval that is the sample point where the height of the rectangle is determined. And it's determined by the function f of x. Right? So this is the curve f of x. And at that particular sample point, x bar indicates the sample point, the k represents which of those subintervals is being used. So it's the kth subinterval, and x bar is the sample point, and we're evaluating the function at that particular sample point to establish the height. The height comes from the function, and the height, in this case, is the height of this shell that's kind of like a cylinder. It is a cylinder, and so you could also refer to it as a cylindrical shell wall. And that particular shell wall has a volume that comes from the thickness, which is in this case is indicated by this delta x. So there's a thickness, and there's a height, and then there's a length. So how do we find that volume of that one particular blue cylindrical shell wall? Once we have that volume, we could do that for several subintervals on this interval from a to b to break it up and find the volume of each of those shell walls, and all together it would approximate the volume of the actual solid for this whole region as it's rotated around. Let me try to show another picture of that. Okay, so I have a little app running here in Mathematica that shows a curve that would be the f of x, and broken up into 10 little subintervals. Each of them has a height that's given by the function. In this case, it looks like maybe it's using left endpoints. Then what we'll do is we'll imagine rotating it around this vertical axis. Looks like it actually says z there. So when that gets rotated, we produce this solid that is shown here like this. Now we would typically rotate all the way around the axis, and this app, it just goes halfway, it stops at pi radians. But that's the rotation that we're imagining, and we can actually see it as like this, where each of these are the shells that we calculate the volume for, and adding the volumes of all those shells gets me a real good approximation to the exact volume of the solid. So imagine increasing the number of segments into which finally in the limit, when those widths become infinitesimal and we are continually summing all of those volumes, we get the actual volume of a solid. All right, so let's go back and look at exactly how would you find the volume of one of those shells. Well, the shell is being rotated around a y-axis in this image, and so you can see that we could take x to be the radius of the shell, and it really becomes just x in the limit of skinnier and skinnier widths. So So the actual volume of that shell, you could think of it as sort of stretching it out into a rectangular solid, as we can see here. And you see that its length, because it's rotating around the y-axis, its length is the circumference of the circle with a radius of x. The width of the shell is that delta x, and the height of the shell is the value of the function at that particular value x. So I'm looking at the volume as length, which comes from a circumference around, that's the length of the shell, the height of the shell, and the width of the shell. And of course this means continually adding these infinitesimally thin shells. Of course this means summation, so it's the summation of all those infinitely thin shell walls from some point A to some other point B on some interval that region is defined, that interval that we're going to rotate around the axis. So by integrating from A to B, we're finding the entire volume of this region as it's rotated around the y-axis. All right, that's the shell method. Now let's see what we can do, a really kind of interesting example using the shell method. The question I want to look at is, suppose you make napkin rings by drilling holes with different diameters through two wooden balls, which also have different diameters. You discover that both napkin rings have the same height h as shown in the figure. So part A would be, guess which ring has more wood in it, or really which has more volume of wood. And then let's see if we can really check that guess by using the cylindrical shell method to actually compute the volumes of a napkin ring that is created by drilling a hole with a radius r through the center of a sphere with radius big R. And when you calculate that volume, we can express it in terms of h and see if we could determine which of these really has more volume. So looking at it, it's really impossible to say. I mean, on the one hand, this seems to have thicker sides, but then this seems to be a bigger overall ball, so maybe that has more volume. It's really impossible to tell. Let's look at this picture a couple more times in different ways and see if we just begin to understand the question, because it is a puzzle. So here's another, I know it's a kind of faint image, but it really helps to emphasize that we're beginning with two different spheres. Imagine drilling through the sphere with a cylinder so that the only thing left is just these sort of regions where these lines are, these vertical lines are. That's, imagine rotating around this cylinder. That's a bit of volume that we want to identify. What is that volume and how does that compare to this volume? On the other hand, is this maybe less volume because this region seems to be maybe thinner, but it does go further around a larger circumference. So this is a real puzzle, right? We have a sphere number one that has radius 1, and it has a cylinder that goes through it that has radius r1, little r1. It has a height of that cylinder h. And over here, this is a different sphere with a different radius and a different cylinder that's been drilled through it, leaving a remaining volume that's potentially different. The only thing that's the same in both of these is this height of the cylinders in each picture. Let's look at it a little bit more. So here's the same two spheres, different radiuses. Big R1 is different than big R2. They just, really, obviously it's completely obvious that the sphere on the left is smaller, right? This radius is absolutely completely different than that radius, right? They're obviously different lengths. And the cylinders are quite obviously different radiuses for these cylinders. And the only thing that's the same in these two pictures is this height of the cylinder, right? There's two completely different spheres with different cylinders drilled through them that leaves a bit of volume in each of them. And I'm wondering about the volumes in each of these two spheres, the volumes that remain, and wondering whether one is more than the other. So here's another picture. Smaller sphere, radius big R1. Through it, imagine cutting out a cylinder so that the only thing that's left is this napkin ring. Right, so this is the sort of image that we are imagining when we talk about a napkin ring. It's this result of taking a sphere and drilling this cylinder through it. Like here, looking from the side, two different spheres, each of them with two different radius cylinders. They could be any radius, but the heights in both of them are the same. Wikipedia has an entry on this particular topic, and I think it's a pretty fascinating image right there. These are several different napkin ring possibilities, sort of trying to figure out what I'm looking at there. It's sort of like the napkin ring hasn't been completed all the way around. I'm not sure why, but it's just we're looking at different spheres with different radiuses and cylinders that are different in each case, but the height remains the same in each of these. Okay, so now are you finally ready to calculate the volume for this thing after all that buildup? Let's actually calculate the volume of this napkin ring. So we'll look at a picture like this. I'm only going to consider the top half of a napkin ring and compute volume for that, and then just double it because I know the symmetry about the x-axis, that it would be the same underneath the x-axis as it is above. So we only have to do this part above the x-axis, finding this volume of this region in here that's being rotated around the y-axis. So let's begin with an xy axis, and let's get some radius r for our sphere. Alright, so now I've drawn myself a portion of the sphere in the first quadrant. The sphere has a radius of r. You can rotate it around the y-axis, and you can rotate it around the x-axis to actually get that sphere. And somewhere here we have a cylinder that has a radius little r. So whatever radius might be chosen, once it's cut through the sphere, intersects at some point on the circle. So once the radius of the cylinder is chosen and the cylinder is drilled through the sphere, it'll cut through the sphere at some point on the surface of the sphere. Now that means that it's going to be this region that we will need to rotate around the y-axis. We'll get a volume in that process. We'll take that volume and double it to get the volume of the napkin ring. So what's this curve? This comes from a circle with a center at the origin, so the equation would be x squared plus y squared equals big R squared. If we solve for y and take a square root of both sides, and I'll just use the positive only because I'm going to assume positive values for y in this portion of the curve. Right? So y is positive in this interval, in this region that we're going to rotate. So the function that I want to work with is this f of x equal square root of big R squared minus x squared. Now, in order to find the volume with the shell method, you can think of any point x corresponding to some height y that, well, you could even imagine here a little representative rectangle, just for a minute to go back to the shell method. There would be a representative rectangle for that region that would produce a shell when you rotate around the y-axis. So what is the volume of that region? By the shell method, it's an integral from x equals little r to x equals big R. That's the interval I'm integrating on. 2 pi, because we're going to rotate all the way around the y-axis. 2 pi x, because x is actually the radius of the shell. F of x, in this case, is a square root of r squared minus x squared, and I'm integrating with respect to x. I have widths of shells that become dx in this infinite summation. So that's the volume of just this region. Now when I actually want to calculate the volume of the napkin ring, I need to put an extra 2 on there. So the 2 is to calculate the volume below the x-axis as well. It's symmetric with the volume above the x-axis. And this integration here is the volume. This is the volume when the shaded region in the diagram is rotated about the y-axis. All right, so then let's see where we can get with this integration. We've got a 2 pi constant here. Let's take that out in front. Integrating from an x value of r, little r, to an x value of big R, x square root r big R squared minus x squared dx. This is an integration we can do with substitution because I know the derivative of what's inside is 2x, or negative 2x, and that'll cancel with this x here. So let's use a substitution. U equal big R squared minus x squared. So du would be negative 2x dx, and we can switch out the differentials that way. In fact, let's just do this extra step here of solving for dx. So when you go back to substitute everything in terms of the new variable of integration, when x is little r, then u would be big R squared minus the value of x, which is little r squared. And then the upper bound of the integration, when x is big R, you've got big R squared minus big R squared, u is equal to 0. I'm going to just copy the x for the moment. Square root r squared minus x squared is exactly u, and then the dx can be replaced with this differential du divided by negative 2x. Well, the whole reason the substitution was chosen was because these x's get canceled out in the integration, so everything is in terms of u. That's a good sign. A neat little trick I can play here is, because of the negative, I can factor the negative out. I can factor the negative 2 out. But what I'd like to do, just because it's possible and it's a good chance to show this at work here, I'll just drop the negative and switch the bounds of integration, and I'll also cancel the 2 with the 4. So I end up with 2 pi. And because I dropped the negative, this will go from u equals 0 to u equals big R squared minus little r squared. So I just switch the bounds. Okay, now that's an easy function to find an antiderivative for, which is the power rule. So 2 pi. Antiderivative would be u to the 3/2 power, because this is u to the 1/2 power. So you add 1, you get 3/2. Divide by 3/2. Power rule. And then we're going to plug in the bounds. So when you flip the 3/2, you get 2/3. So we get 4/3 pi. And now we're also going to plug in the bounds. So let's go with r squared minus little r squared with a 3/2 power. And then, of course, minus 0 when you plug in the 0. So right now we're looking at the volume is 4/3 pi big R squared minus little r squared to the 3/2 power. So that's a good formula to calculate the volume if you knew the radius, the radius of the sphere and the radius of the cylinder drilled through it. This would tell me the volume. But there's a little more. The question specifically said let's see, let me go back to the question. Question specifically said, use cylindrical shells to compute the volume of the napkin ring created by drilling a hole with radius little r through the center of a sphere with radius big R, and express the answer in terms of h. So we've got a little more to do here. and it'll answer the question about which one of those was a bigger volume. If I'm at this point, I want to write this in terms of h. So where does h figure in this picture? Let's go back. Remember, h was the height of the cylinder. So actually this here, this is h over 2. Now I can relate h with the value of little r and the value of big R because it's possible to identify the radius of the sphere in one other place, right here. This is a radius as well. This red segment here represents once again the radius of the sphere, just like I have here. This is the radius, and little r is the radius of the cylinder, and now we actually have a right triangle in here. So it's possible to connect the big R, little r, and the value of h with the Pythagorean theorem. This is little r. The length h over 2 is another side of a triangle, and that's equal to the hypotenuse squared, which is big R. So solving for h, I'd say h over 2 squared is big R squared minus little r squared. And now we can use that and go back to the formula we had derived for this volume of this shaded region, right? As this whole region now, as it gets rotated around the y-axis, I have the volume for that region already computed down here, and I've expressed it in terms of this r squared, big R squared minus little r squared, but that's exactly h over 2 squared. So we have 4/3 pi h over 2 squared, all raised to a 3/2 power, and then these guys cancel. 4/3 pi, this will be h over 2 cubed. That's 4/3 pi h cubed over 8. So finally 1/6 pi h cubed. This is a formula for the volume, so it's completely independent of the values of big R and little r. And that's amazing. How is it that that volume doesn't depend on the radius of the sphere and the radius of the cylinder drilled through it? They could be anything. All you need to know is the height. That's just really mind-boggling. Like, wait a minute. As long as you have the height, you have the volume. All you need, this is actually, in this picture, this would be h over 2. But if you know the height, then I can get the volume of this region that's rotated around by simply knowing the height? What? How does that make any sense? And so both of these must actually have the same volume. It depends only on the height. What? I swear, I understand it. At the same time, it's a complete mind-boggling result that volume is going to come out the same no matter what the sphere radius was and no matter what radius cylinder you choose inside it, as long as it works out to be the same height in the resulting figures, in the resulting napkin rings. As long as they have the same height, they have the same volume. It's just silly. It's amazing, fascinating, logically correct, almost sort of paradoxical that we follow this logical process to get this result that it doesn't seem really logical, but there it is. Volume can be determined simply by the height alone. The volume of the napkin ring formed in this way is determined only by the height. Okay, that's the end of the video. I hope it was interesting and helpful.